also ask him to join.
I know, sir. I know.
Okay.
because I pursued PhD from NIT Trichy.
Yeah.
Yeah, that time he was a BTech student. I know. Pranesh and Rakha, both I know.
Yeah, yeah.
Pranesh,
Raghav,
your microphone is muted.
yeah. So Raghav is
Oh,
down the
yeah.
back. Yeah.
Yeah, Dr. Asha was the instructor for a lot of my courses, so I do. Yeah.
Yesterday I was sharing with my HOD also the same thing. Welcome, Parthakayal, sir. Good morning, sir.
Morning.
Sir.
Good morning, sir. Good morning, sir.
Good morning, Dr. Peng.
Oh, good morning. Morning.
Yeah, Jimmy. Hi.
Or,
Yeah.
so then everyone is present now. Possibly we'll start quickly.
Yeah.
Assam, Assam, everything fine from this side?
Yes, sir. We
Okay.
started already broadcasting. Yeah, please, sir.
Done. Respected Director, Sir, Professor Sivaji Bandyopadhyay, our guest speaker for the technical session, Professor Zimi Peng from National University of Singapore, Dr. J.P. Mishra, Head of the Department Electrical, Dr. Sukumar Poti, TechUp Coordinator, all the faculty members of Electrical Engineering of NIT Silchar. I welcome all the participants, including the participants from faculty members, research scholars, and the students across India. We are extremely pleased and honored to cordially invite you for the one-day webinar on global renewable energy generation scenario and challenges in microgrids, organized by Department of Electrical Engineering and IT Silchar under the aegis of TechUp3. This particular workshop was planned in the last month, and Honorable Director Sir also approved to conduct this particular course a month ago. Today we are here to listen from him on the global renewable energy generation scenarios and the challenges in the microgrids in his session. Dr. Jimmy Chain Peng is currently an assistant professor with the Department of Electrical and Computer Engineering at National University of Singapore. In 2013, he was appointed as the visiting scientist with research laboratories of electronics at the Massachusetts Institute of Technology, Cambridge, Massachusetts. And from 2014 onwards, he is a visiting assistant professor at MIT. Previously, he was a part of a startup team at Master Institute. Now, he is a part of Khalifa University, United Arab Emirates. He is currently the secretary of IEEE PES working group on high performance computing on power grid analysis and operation. Since 2020, he has been nominated to serve on the Singapore Standards Council, a body approved by the establishment, review and withdrawal of Singapore standards and technical references. He is also a committee member for Spring SS 535 standards, that is the code of practice for installation, operational maintenance, performance, and construction requirement of mains failure standby generating systems. Spring is an agency under the Ministry of Trade and Industry Singapore. Previously, Dr. Peng served on the Standards New Zealand, a business unit within the Ministry of Business, Innovation and Employment New Zealand. He was also nominated by the IEC National Committee of New Zealand to join the IEC Young Professional Program in 2011. We welcome Professor Peng for today's lecture. As a brief note about the program, we have around 911 participants registered for this course, out of which 427 are from faculties, including IIIT Bhubaneswar, Jadavpur University, NIT Agartala, NIT Silchar, JNTU Hyderabad, and all the state colleges and government colleges across India. We have 37 industrial delegates from DRDO, Central Board of Irrigation and Power, Central Electricity Authority, CSIR, Sajlon Limited, Kochi Metro Rail Limited, Birla Group, TUB, KLB Instruments, Alpha Electric, then Care Private Limited Chennai, Parker Hanif India. We have around 447 students, participants for this course, mostly from IIT Delhi, IIT Madras, IIT Bombay, IIT Roorkee, IIT Bhubaneswar, IIT Gandhinagar, IIT Dhanbad, IIT Mandi, and IIT Hyderabad. Similarly, from some NITs like Trichy, Hamirpur, Silchar, Rourkela, Patna, Meghalaya, Nagaland, Manipur, MNIT Allahabad, Srinagar, Uttarakhand, Surat, Delhi, Sikkim, Jamshedpur, Goa, Meghalaya, and Kurukshetra. From Central University, from Karnataka and Tezpur. Then we have from Gujarat Technological Universities, from Jamia Millia, from Jadavpur University, and most of the universities and colleges from across India. Now I request Dr. J.P. Misra to deliver the welcome address for this session very quickly. Over to J.P. Misra, sir.
Thank you, Professor Nalin Dev Chaudhary, sir. Honorable Director, NIT Silchar, Professor Shivaji Bandyopadhyay, Honorable External Expert and Guest Speaker, Dr. Jimmy PEng, Assistant Professor, Department of Electrical and Computer Engineering, National University of Singapore, Singapore. Respected Techie 3 Coordinator, NIT Silchar, Dr. Sukumar Pati, esteemed faculty, colleagues, dear participants from different teaching institutions as well as industries all across India. On behalf of Department of Electrical Engineering, NIT Silchar, I extend a warm welcome to all of you in this inaugural ceremony of the one-day webinar on global renewable power generation scenario and challenges in microgrid, organized by Department of Electrical Engineering under the sponsorship of Techie3 NIT Silchar. We are very thankful to our director, Professor Shivaji Bandyopadhyay, for sanctioning this webinar for the Department of Electrical Engineering with the support from our Techie3 coordinator, Dr. Sukumar Pati. As addressed by Professor Nalin Dev Chaudhary, sir, the coordinator of the webinar, about the main objective of the webinar is to focus on global renewable power generation scenario and various challenges, issues those are faced with the integrating and controlling renewable source with the conventional grid as well as microgrid under varying source conditions, non-ideal grid conditions, as well as varying non-linear and linear load conditions. Also, the recent trends towards the distributed energy systems and integration of renewable sources to the autonomous micro and nano grids, which require specific power electronics control capabilities for its reliable and secure operation. Presently, we have with us Honorable External Expert and Guest Speaker Dr. Jimmy PEng, Assistant Professor, Department of Electrical and Computer Engineering, National University of Singapore. I thank you, sir, for accepting our invitation for delivering a talk with your intense expertise to make this program more interesting and informative. I hope several issues with respect to various design, operational, and control aspects associated with microgrids will be addressed by you, sir. As informed by coordinators, there are more than 900 participants have registered for this webinar, including the faculties, industry delegates, and students from across India. Hope this webinar may provide unique opportunities to all the participants in developing the new idea and avenues for doing research in the area of microgrid control. My best wishes to all the coordinators, Professor Nalin Dev Chaudhary sir, as well as Dr. Asarani madam, for a grand success of this webinar. Thank you all again. Over to Dr. Professor Nalin Bihari Debchodhary, sir.
Thank you, JP Mr. Sir, for your nice welcome address. We are really happy to have you as our HOD and having a warm welcome address to all our guests. Thank you, sir, again. Now I request Dr. Sukumar Poti to deliver his special address for this session very quickly. Over
Thank
to
you,
Poti.
Nalin sir. Good morning to one and all. Respected Honorable Director sir, Dr. Jimmy PEng from NUS Singapore and speaker for this webinar, Dr. JP Mishra, Head Electrical Engineering Department, Professor NB Debchodhary, my esteemed colleagues from NIT Silchar and other institutes, and dear participants. At the outset, on behalf of Coordinator TECIF3, NIT Silchar, and my own behalf, I congratulate Professor MD Debchodhary and Dr. Asarani MA, coordinators for this program, for their initiative to conduct this webinar on global renewable power generation scenario and challenges in microgrids. I am sure that all the participants attending this webinar will get benefited through sharing of useful and relevant information by the expert and have a fruitful discussion. I am happy to share that this is 23rd online program organized by different departments of NIT Silchar under TECIF3 during last 2 months, and 5th one by the Department of Electrical Engineering. I believe that through the conduction of online program like this, the new avenues of research collaborations will open through interactions with researchers of other premier institutes like NUS Singapore. Once again, congratulations to both the coordinators and all the participants. I wish a grand success of this webinar. Thank you. Over to Nalin sir.
Yeah. Thank you, Sukumar sir, for your information related to TQ fund and incineration. And we are really happy to have the 5th program today with us. Now I request our Honorable Director, sir, Professor Sivaji Bandyopadhyay, for his inaugural address. Over to sir.
Yeah. A very good morning to Dr. Peng. Hi. My colleagues from NIT Silchar, colleagues from other institutes, PhD students. So in the series of the webinars, which has become a practice during this pandemic period, obviously we are trying to always get connected more and more in new and new state-of-the-art research areas. It is in this series that is we have Dr. Peng with us, and in the area of global renewable power generation scenario and challenges in microgrid. Now, before deliberating on the topics, I will give a brief overview of the NIT Silchar itself. But before that, let me share with Dr. Peng that 2 of my direct students are at the CSE department at NUS Singapore. So obviously, and currently also, and in between, many of my students, they got their PhD degree there, and from there they shifted to other institutes as well. So personally speaking, I have a warm relation with the National University of Singapore. Now, NIT Silchar is one of the 31 NIT or National Institute of Technology in India. Every state in India has an NIT, and we are one of them. We are an old institute. In 1967, NIT started. And at present, when you look into the ranking scenario at the national and the international level, obviously our ranking is no match for the ranking of National University of Singapore. But the thing is that is if we consider the current scenario and how we are actually progressing, so that will give us an idea. And as I say always, that is ranking gives us an assessment of the current position of an institute. So at say we have research and innovation as our key focus in our pursuit for excellence, in our pursuit for getting ranked also. And in the research innovation, we focus on the interdisciplinary research area, collaborative research, international collaborations, as well as the industry collaborations as well, so that our research becomes meaningful and we are able to contribute to the society at large. Uh, our colleagues, they work on different research areas, but we have identified some core research areas and we put trust on those areas, so that these research groups, they coordinate among themselves within the country, outside the country, in the continent itself. So one of them is the natural language processing, second is water resources, third is energy science and technology. Obviously, this current today's talk is also part of that area. And the fourth one is the medical imaging and technology. That is, though you do not have a medical, say, the section or a faculty in the institute, but our colleagues are doing excellent activities in this area in collaboration with the doctors and other medical practitioners all around the country as well as around the globe at the same time. We put a lot of focus on the undergraduate research, so that our undergraduate research, when they pass out, they are ready for their, say, the higher education in other institutes across the globe. And I obviously would expect that maybe by very soon, some interested pass out students from NUS, from NIT Silchar, will find a place to do his higher studies with Dr. Jimmy PEng at NUS and with other colleagues as well. Because we understand that the technology is changing so fast, so that what the student studies in the 4 years of study, maybe in the bachelor program, by the time he or she passes out, so the things become actually completely changed. So they need to be aware of that is what is happening, what is the state of the art. And so we involve them through different ways, through their projects, through such kind of webinars, through some visits, talks, etc., so that our undergraduate students as well as our postgraduate and the PhD students, they are aware of the current situation. We have a very large number of PhD students, and in the last 2.5 years, we have almost doubled the number of PhD students from around 400. Currently, we are around 800 number of PhD students, so that our faculties and the PhD students, they can work in diverse areas, and this kind of collaborations with colleagues abroad and all over the globe. So that brings new and new research problems to our case. And obviously, in that pursuit, we understand we need more and more research students at the same time. Now, I started talking about ranking. So a brief idea: at the national level, in the engineering institutes, we are in the 46th position. In the overall institution category, we are in the 94th. In the national innovation ranking, we are in the rank band of 11 to 25. And for the first time, NIT Silchar has been able to find a place in the Times Higher Education World University ranking. So obviously, as a starting, we are in the rank band of 801 to 1000. And among the Indian universities which took part there in that ranking, so we are in the 19th position. And as I say that we view ranking as our SWOT analysis, identify your strengths, weaknesses, opportunities, and challenges. And very soon we'll be going to recruit base level faculty members also. So we'll be sending requests to our the collaborators like Dr. PEng and others, so that Indian PhD students or postdocs who are completing their study at their respective places, so if they want to return to India, they can think of joining NIT Silchar as one of their places. So that depends on that kind of collaborations that you are pursuing, because in our current set also, we have good number of people who are have done their PhD or their postdoc either in best of the Asian institutes or across the globe as well. So we, in order to reach the excellence, so we want to have more and more number of say the pass out PhD students and the postdocs also, so that they can join us and we can share their work. So that is one request and one relationship will start. But at the same time, the current relationship in the area of, because say renewable energy and microgrid, as I see, that is NIT Silchar puts a lot of thrust on the renewable energy also, and what might be already shared with Dr. PEng is that we have an 1 megawatt rooftop solar power plant, and this area is being in the subtropical region, receives a lot of sunlight as well as a lot of rain at the same time, lot of wind with a high speed at different times of the year. So renewable energy has got a high potential in this region. And what our statistics was showing in the last 1 year, almost say 30% of our energy requirement was supplied by the renewable, the solar energy. And in fact, we are able to supply excess power into the state grid as well. Now, microgrids and renewable energy, they are interesting research issues. I'm from computer science engineering area, so obviously I'll not delve much into this area. But as I understand, because the reliability of renewable energy generation, so that is a very crucial issue. It is not something with the traditional power generation. So frequency of the power generated, so that will be an issue. So the microgrid synchronization, then the interaction among the microgrids also. So that becomes another issue, like the distributed power generation, what Dr. JP was talking about. So all these research issues, and in the current world, when India is spearheading the international solar movement, so I understand that is a lot of deliberations on the research level and at the ground level are necessary to make the solar power accessible to the society as well. And in that, this distribution becomes important. So today's talk on microgrid and the interaction among the microgrids, more specifically with renewable energy sources, that becomes more significant. So with this, I wish today's program a grand success, but I wish that the program or the relationship will not end today. It will continue for the future. Thank you.
Thank you, sir.
Sir,
Please.
thank you very much, sir, for your nice inaugural address. Now I request Asarani ma'am for vote of thanks and invite PEng for his next session. Over to Asarani ma'am.
Thank you so much, sir. Thank you, Naling, sir. A very good morning to one and all present here. Our Honorable Director, sir, National Institute of Technology, Silchar, Professor Shivaji Bandyopadhyay, sir. Our Chief Guest and Eminent Speaker, Dr. Jimmy PEng, National University of Singapore, NUS. TechUp3 Coordinator of NIT Silchar, Dr. Sukumar Pati, sir. Our beloved Head of the Department of Electrical Engineering, Dr. JP Mishra, sir. My dear colleagues and dear participants, it's my privilege and immense pleasure to propose a vote of thanks in this inaugural ceremony of the one-day webinar on global renewable power generation scenario and challenges in microgrids, organizing by the Department of Electrical Engineering in NIT Silchar. On behalf of the organizing committee and on my personal behalf, I express my sincere thanks to our Honorable Director, sir. We are extremely grateful to you, sir, for your presence, motivation, and words of encouragement, and for giving consent to organize this webinar. Your able guidance and support is always a motivation for us, sir, to excel in both academic and research front. We express our heartfelt thanks to you, sir, for your suggestions and continued support in every aspect. Thank you, sir. Now we extend our gratitude to Dr. Sukumar Pati, sir, TechUp Coordinator and NIT Silchar, who has given the consent to organize this webinar and also for providing us the necessary financial support to conduct this program. Thank you, sir. So now we would like to extend our sincere thanks and gratitude to the Chief Guest and the eminent speaker, Dr. Jimmy PEng, National University of Singapore, US, for sparing his valuable time with us in this inaugural ceremony and also for being kind enough to accept our request to deliver the expert lecture during this webinar, even in his busy schedule. Thank you so much, sir. Now, we would like to extend our sincere thanks and gratitude to our beloved HOD of Electrical Engineering Department, Dr. J.P. Mishra sir, for his valuable suggestions and guidance to organize this webinar in a professional way. Thank you, sir. Also, we acknowledge the help and support provided by our institute, NIT Silchar, and also by our Department of Electrical Engineering in this venture. So, most importantly, I would like to extend my heartfelt thanks to my co-coordinator and our previous HOD, Dr. Nalin sir, for the continuous support for the program till today. Now, I would like to thank my colleagues, research scholars, students, and my dear participants. And even I can see here Burman sir. Thank you for joining, sir. So, I would like to welcome all the participants from our institution and from different organizations across India for joining this inaugural function. So, thank you all. Now I am moving on to the responsibility of welcoming our chief guest and eminent speaker, Dr. Jimmy Peng, National University of Singapore, to this webinar. It's my privilege and honor to welcome Dr. Jimmy Peng, Assistant Professor, Department of Electrical and Computer Engineering. Added to that, he is actually a recipient of several awards and affiliations, which starts from the best reviewer, best faculty of NUS, and lot more. And he has completed 5 sponsored research projects under the Ministry of Education. Then it's from the NUS and Humboldt University, Berlin. Then in collaboration with MIT and Mazar Institute, like cooperative program, almost like it worth 57 lakhs in good dollars. And he is currently serving as PA for 3 ongoing projects, which includes the data networks and cyber physical systems, future resilient system program, National Research Foundation, etc. So he had more than 75 publications in different international reputed journals, which includes almost all the IEEE journals like Industrial Electronics, Power and Power Delivery, Industrial Informatics, Sustainable Energy, Power Electronics, etc., etc. Under his eminent guidance, already 4 students completed PhD and 4 scholars are pursuing now. And basically, his research interests include network stability and control, focusing on data analytics and control theories for managing microgrids, distributed generation, etc. And he is also working in the area of security of cyber physical systems and design and demonstration of resilient topologies to facilitate energy saving and grid support services. He is a renowned academician and researcher who has provided many significant contributions in the area of interconnected microgrids and cybersecurity. So now I request our Honorable Director, Sir, NIT Silchar and Chief Patron to declare the webinar is open. Please,
Yeah, I declare the webinar on global renewable power generation scenario and challenges in microgrid to be delivered by Dr. Jimmy Peng open. So let's enjoy. Thank you.
yes, sir. Thank you so much, sir. Thank you, sir. So thank you once again thank you for all the dignitaries who have gathered here for attending this inaugural function. So now, once again, warm welcome, Dr. Jimmy Peng. So now I request Dr. Jimmy Peng to start the session.
Okay, so I will be sharing a window. So,
Sir, actually,
can you see the?
Yeah, yes, we can see.
So, are you able to see the screen, the slides?
Yes, sir, we can.
Okay, so I mean, thanks very much for the warm introduction and also the speeches. I'd really like to thank NIT, for your invitation, and also Dr. Asha for reaching out to me in the first place. So our research at National University of Singapore focuses on grid resilience and security, where we investigate the stability and control of microgrids, as well as the grid vulnerability to various types of attacks. Now today, I will be presenting some of the findings of the former research, specifically looking at the control of Droop control inverters within the microgrid for facilitating stable power sharing. So this seminar will be divided into the following subsections, where we will begin with a review of power engineering fundamentals, then progressing into the more exciting topics of ensuring stability in the presence of line dynamics and coupling effects of the real and reactive power. There are issues that are usually neglected from the classic power system stability analysis because of the inductive nature of the lines in the high voltage transmission systems. However, microgrids are predominantly deployed at the lower voltage side, making the use of these assumptions questionable at times. And in some cases, these assumptions can trigger power sharing issues among grid-forming inverters in an islanded or autonomous grid. So before diving into the topic of grid-forming inverter, I would like to take this opportunity to briefly outline our testbeds and research areas within my group at NUS. Over the past 3 years, we have been constructing 2 microgrids for validating our research. We have one 21 kilowatt system, which is primarily used for research projects, and have another 6 kilowatt version that is designed for graduate teaching purposes, as shown on these diagrams. In my group, all research on microgrid stability are validated in numerical simulations as well as hardware experimentation. This allows us to ensure the developed control solutions are practical and scalable. Our research in microgrid resilience focuses on the objective of power sharing. That is, ensuring the generation equals to the demand, which is a key principle of power system operation. Currently, stability analysis of Droop control inverters is conducted by my PhD student, Panesh Rahman. And meanwhile, deriving stability properties of microgrid using graph theory is carried out by another student of mine, Andrei Gorbanov. In parallel, our research in grid security emphasizes on preventing cyber attacks and behavioral attacks. Mitigating cyber attacks in microgrids is being carried out by Jinqiu Zhang. And lastly, preventing of disinformation attacks on the distribution system is being executed by my other PhD student, Raghav Raman. As of today's topic, I'll be talking about stability analysis of Droop control inverters. Oops, sorry, just give me a second. I have a technical problem. Okay, I'm just coming back. Sorry about this. Yeah. Give me a second. Sorry. I'll be back. I'm almost there. Okay, so I think we're good. Okay. Sorry about that. Now, so what is microgrid? The US Department of Energy defines a microgrid as a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid. Well, things are relatively simple when a microgrid is connected to the main grid. Any power imbalances can be sourced or synced from the utility grid, and thus eliminating the stability issues associated with the power sharing. On the other hand, when a microgrid is operating under islanded or autonomous mode, it needs to manage all the dynamics triggered by the imbalance itself. In essence, we need to coordinate generation resources, electrical loads, and possible storage within the microgrid in a near real-time environment. This is a complicated problem, as a microgrid can consist of a mix of generation profile, including synchronous generator, inverter-based generators, and electrochemistry storage devices. But more importantly, the classic concepts we learned from power engineering textbook may not be suitable, considering a microgrid has a high RX ratio of which exhibiting strong coupling between the active and reactive power components. Now, when I first explored microgrids a few years ago, the first question to ask is, why microgrids? I mean, why bother tolerating these power sharing issues when we can just tap off the main grid? The question can be associated to 3 elements, of which are driven by the cost and resilience. Microgrid allows customers to install renewables, which can help to reduce the amount of electricity used from the power utility, as well as minimizing the carbon footprints. These renewable generations, along with the energy storage, can boost the load reliability, which ensures uninterrupted supply of power during emergency conditions in the main grid. As we know, load sharing is carried out based on a priority list. As commissioning microgrids in the residential or commercial or education sectors makes sense because these sectors are generally not considered on the top of the list. As a result, the financial losses due to power outages can therefore be reduced. Leveraging on the generation profile, storage, and load management, microgrids can also participate in grid auxiliary services such as demand response and frequency regulations. Basically, microgrids can serve as an effective mechanism to tackle power balancing problems at the end user side, as well as serving like synchronous condenser to provide reactive support. In a way, they help to make the main grid more resilient and in return take the pressure off the utility. In general, microgrid empower the end users to become more independent and thrive for a more sustainable grid operation philosophy. That is, establishing responsibility symbiosis between utility and customers, which is my opinion is the most cost-effective solution to achieve a grid resilient in the era of deregulation. Furthermore, the benefits of microgrids can be summarized as follows. When they are grid connected, the overall reliability of the power system can be enhanced. In autonomous mode, they can ensure reliable supply of electricity to consumers in an isolated environment, such as on the island of Alcatraz or on the icy continent of Antarctica. As we know, ensuring supply of electricity to all those 100% of the time is extremely expensive. So most microgrids will also devise their own priority loads. Therefore, in the event of grid emergency, microgrids can serve as additional insurance policy for critical loads. Lastly, the adoption of renewable generations can reduce the dependence of fossil fuel, which is becoming more expensive due to the heavy environmental fines and volatile hydrocarbon markets. So a microgrid can operate under two different modes, that is, grid-connected mode and islander mode. Under grid-connected mode, the frequency and voltage regulations are managed by the utility grid. In other words, all inverters within the microgrid are simply following the main grid. One operational benefit of doing this is that all instability within the microgrid can be suppressed and handled by the utility network. On the other hand, islanded mode refers to when the microgrid has to provide its own voltage and frequency regulations. This is achieved by incorporating additional control loops in some of the inverters, and one popular method is Droop control. Under islanded mode or autonomous mode, all instability issues must be handled by the grid-forming inverters, which are taking the role of the utility grid. Things become quite interesting under islanded mode, and this has sparked much research in addressing the microgrid stability in the context of regulating and power sharing capability. Different to a utility grid, a microgrid will most likely have a significant smaller net inertia due to the absence of large synchronous generators. We can imagine inertia as a buffer that helps to buy operator time to react to transient events within a power grid. Now, a low inertia system will exhibit a relatively faster transient response in the context of frequency variation, which can trigger protection relays if dynamics are not properly mitigated. A typical microgrid will have a rate of change of frequency in the range of a few kilowatts per 0.1 hertz. Whereas if you look at the US, the Eastern interconnection has 2,760 megawatts per 0.1 hertz drop, or 1,482 megawatts per 0.1 hertz drop for the Western interconnections. So typical monitoring, analysis, control philosophies of running a power grid may not be suitable for a microgrid scenario. Since microgrid usually consists of multiple inverters, we will assign some of them to provide grid-forming functionalities. However, the capability of an inverter to regulate the entire microgrid is limited due to its ratings. But assigning all inverters to operate in grid-forming mode may actually not be an attractive financial option. Note that the voltage and frequency regulations are the outcome of the disturbances, where controllers are attempting to restore equilibrium between the power generation and power consumption. Basically, the stability and control of a microgrid boils down to power sharing among the generation sources. The challenge is therefore to determine the fundamental nature of power sharing, which leads to the question of how should the power imbalance within the microgrid be managed by these grid-forming inverters. So referring to the fundamentals of electromechanical dynamics, the machine's inertia helps to dampen the disturbances by reducing the magnitude of variation in the system frequency right after a fault or disturbance. In a utility grid, the time frame of electromechanical response is usually in a range of few seconds. However, the adoption of inverter-based generators or low-rating diesel generators mean the buffer zone of inertia will usually be less than a second. As we can see in these plots, the lack of inertia in a power electronic dominant grid can spiral to instability in a more violent manner. In literature, many research papers have reported ways to improve the frequency nadir during a disturbance through mechanisms like virtual inertia. But now, let's say in islander mode, the grid-forming inverters have to take the responsibility to absorb the energy injected by disturbances, which are executed in the form of voltage and frequency regulations. However, the ability of a single inverter is limited due to its rating, and therefore a collection of grid-forming inverters are usually used to dampen disturbances. For instance, let's have a look at the following 3 bus examples shown here. The grid-forming inverter is highlighted in orange color. The amount of current drawn from the inverter is not controllable and is actually governed by the loads themselves. Now, if we introduce a step change in the load 2 to 2 amps, it will then force the grid-forming inverter to provide additional current. Suppose the inverter 1 is rated at 1.5 amps, then this disturbance is sufficient to cause the inverter to overload and leading to an unstable microgrid. Continuing with this example, but now we assign inverter 2 also as a grid-forming inverter. From our basic circuit theory, we can share the power disturbance using the 2 parallel inverters, which in return will be able to prevent the overloading scenario as witnessed in the previous slide. Again, the number of grid-forming inverters is an open question. The choice is dependent on the size and characteristic of the disturbance, network topology, and the rating of the inverters themselves. In practice, inverters can be adaptively set to grid-forming modes based on the needs of the microgrids. A more important question is how should each inverter determine its power output to share the total load? This leads to an important research topic of power sharing among inverters. In fact, inadequate power sharing will cause some inverters to overload or unable to regulate the voltage and frequency in an event of a disturbance. Therefore, the stability of a microgrid is dependent on the power sharing strategy adopted by the inverters. For instance, let's look at the 3 inverter case over here. We are sharing a total load of 3 kilowatts. To ensure each inverter is stressed in a similar manner, we will adopt the concept of Droop. Droop ensures each inverter is sharing at a ratio proportional to its capacity. Depending on the power sharing settings, different stability regions are established. So in the first scenario, shown on the top, a centralized control has been implemented. In essence, each inverter will dispatch its generation output based on commands given by the central mainframe. This is a typical architecture used in the conventional power grids, but may not be suitable for microgrids due to the required investment cost. Now, to establish a centralized control requires high bandwidth communication links, and the required control architecture is not scalable when more equipment are integrated into the microgrid over time. On the other hand, the bottom scenario is where decentralized control has been implemented. In this case, each inverter operates in an independent manner where the output power is governed by the feedback signal from local metering equipment. Now, the key benefits of the decentralized philosophy is the investment cost, and it is a critical design factor in commissioning a microgrid. Here, the inverter-based generations do not require an extensive communication network, which lowers the total cost of construction. In addition, it introduces a notion of plug and play. allowing easy integration of new equipment into the microgrid without the need of major overhaul in the microgrid operation. So to summarize, the key advantage of decentralized power sharing are improved reliability in the context that the inverter-based generators do not need to depend on a communication network. The plug-and-play nature of this decentralized control enables equipment to be installed or removed without imposing major changes to the existing operating framework. And these lead to the third benefit of being scalable to accommodate many equipments over a period of time. Regarding to proportional power sharing, Droop in terms of PF and QF can be deployed. The concept of Droop is actually borrowed from the classic power engineering, where the output power is varied based on the variation in frequency, or the output reactive power is varied based on the voltage deviations. The rate of response is defined as a gain, which is KF for the PF Droop and KV for the QV Droop. Suppose we now have two inverters regulating the grid frequency. Under steady state, F1 equals to F2. This implies that KF1 times P1 will equal to KF2 times P2. Now, by rearranging the relationship, we can conclude that the active power shared by each inverter is inversely proportional to its Droop coefficients. There are other options for decentralized power sharing, but Droop control is perhaps the most simplest, and its principles are analogous to those used in the governance system of synchronous generators. That said, to facilitate more distributed energy resources in the microgrid, the control design should consider aspects of plug-and-play, decentralized control, stability, and contingency handling. The transition should not demand significant hardware upgrades and be adaptive to a range of operating conditions. So now, the task of grid-connected mode inverter is to control current into an established voltage, whereas the task of islanded mode is to establish that voltage. Suppose we have a two-bus network consisting of one grid-forming three-phase inverter and the infinite bus as shown in the single-line diagram. The power measurements are computed from the voltage and current measurements in the DQ domain. Now, the Droop equations can be represented in the following control block diagram on the top. To make the Droop loop more robust to harmonics and high-frequency noise, measurements are passed through a first-order low-pass filter, as shown. The frequency of interest for Droop control is typically in the range of 2 to 10 Hz. To ensure adequate time-scale separation between the voltage Droop loop from the switching frequencies, the voltage Droop loop here defines the voltage reference that is used as the input to the outer control loops of the inverter. So they are reasonably well decoupled because of their different time constants. The slower output voltage loop sets the reference current to the faster intercurrent loop. This is achieved by tuning the PI controller gains in these loops. If the current demand generated by the outer control loop is limited, then the inverter will not be subjected to excessive current. The angle used to convert between ABC and DQ corners can be obtained from the frequency Droop loop. Finally, the output is transformed into the firing pulses. Now, we need to ensure adequate time-scale separation between the outer and inner loops such that the poles associated to each loop do not interact with each other. The typical bandwidth of dynamics of the Droop controller, voltage controller, current controller are fractions of the switching frequency of the SPWM as listed in red. In our case, we ensured the timescale separation between each controller in the order of magnitude of 10. This allows the control loop to be designed independently. Furthermore, well-designed voltage and current loops can be viewed as ideal elements with unity gains, which makes the inverter behave like an ideal voltage source. As a result, the dynamics of the cascaded loop are dominated by the Droop control loop. Under this situation, we can ignore the less dominant elements during the modeling process and reduce the order of the inverter. So let's look at the design of the individual control loops within the inverter, starting with the current control loop shown in the diagram here. The control variable of interest is the line current sourcing from the three-phase inverter. So we can ignore the load control block and focus on the current controller and the low-pass filter. Now, the current loop adopts a PI controller that regulates the current passing through a first-order low-pass filter with an impedance RF and LF. We can cancel the effects of RF over LF by making KI over PI equals to RF over LF. This helps to cancel the undesirable dynamics of the original system and allowing us to manipulate the remaining response. The remaining part of this closed-loop system is actually a type 1 system due to which the steady-state error of the current will be 0. As a result, the transfer function would take the following form, where the bandwidth of the integrator is KPI over LF. Finally, we need to ensure a timescale separation with the switching frequency, such that the control bandwidth should be 2 pi times the switching frequency divided by 10. Equating these two expressions, we can then obtain the controller gain, KPI. Then, using KPI into the first equation, we can solve for KII. The objective of the voltage control loop is to define the current reference for the current control loop. Assume the three-phase inverter is behaving like an ideal current source, and the well-designed current loop is ideal with a unity gain. The transfer function of the voltage controller to the output VDQ takes the following form. We can make the ratio KIV divided by KPV equals to 1 over CF times the R load to simplify the transfer function. Now, as a result, the control bandwidth of the integrator will become KPV divided by CF. To ensure adequate timescale separation between the current controller, we need to make sure the control bandwidth is around 2 pi times the switching frequency and divided by 100. Using the same procedures as before, we can design the gains of the voltage controller accordingly. When we build a detailed model of the three inverters with the grid forming capability, we found that inverters can become unstable under high Droop gains. This leads to growing oscillatory dynamics during power sharing and has a direct effect on the frequency and voltage as well. That said, the problem causing such instability is not just from the Droop gains, but in fact, a contribution of 3 factors. They are Droop gains, Rx ratio of interconnecting lines, and the number of grid-forming inverters. Looking at the eigenplots, increasing the Droop gain will shift the poles associated with the Droop controllers. This leaves us with a question of how to analyze a microgrid consisting of multiple grid-forming inverters. To start, we need to proceed and build a small signal model, and then study the system stability. The destabilizing effect of line dynamics plays a critical role in the overall system stability. For studying the stability issue triggered by line dynamics, let's adopt a fifth-order model using the generalized Droop control. This model eliminates the cross-coupling effect of the active and reactive components and allowing us to focus on the stability attribute of the line. So let's consider the 3 inverter microgrid supplying 2 loads as shown in the diagram. As we have demonstrated earlier, the inverter model is dominated by the Droop controller dynamics, where other controllers can be neglected due to their relatively faster decay rates. The state-space model of the generalized Droop controller of a single inverter would take the form of a third-order model, where KF and KV are diagonal matrices comprising of frequency and voltage Droop coefficients, respectively. The power flow equation to describe the network behavior is represented by a function of the frequency deviation. On the other hand, the network dynamics can be represented by the right-hand side state-based model. We are not treating the lines as passive components, but are introducing static and dynamic parts to the model, the network dynamics themselves. So we will represent the elements of the admittance matrix as transfer functions of the conductance, G of S, and susceptance, B of S. In this case, the inclusion of electromagnetic dynamics from the line will contribute to 2 more orders per inverter. Combining the generalized Droop control, power flow equations, and line dynamic model, we can construct the 5th order model for the multi-inverter system as shown in the slide. The model accounts for the impact of Rx ratio, which is denoted by the variable rho. This expression represents the characteristic equation of the system, whose poles can be readily obtained by solving its polynomial eigenvalues. Furthermore, we observe that there are 2 possible destabilizing effects arising within a microgrid and highlighted in red. They are system dynamics and cross-coupled system statics. In essence, the overall small signal model of a single inverter connected to the microgrid can be modeled by a 5th order model, which is just an extension of the 3rd order Droop controller with electromagnetic dynamics of the line included. Now, using the 5th order model, as we have established, we can now proceed to examine the factors influencing the microgrid stability. In particular, the tuning of the Droop gains while considering the influence of the interconnection network parameters. The obvious destabilizing effect of power sharing is the frequency Droop gain, KF. For a single inverter case, we can see that the conjugated Droop poles shift towards the right-hand side as the KF gain increases in these plots. This results to instability, where the amplitude of power oscillations grow over time. Now, the voltage Droop pole play a relatively minor role in comparison. As the gain increases, the real pole shifts to the left-hand side of the plane, but this also triggers the frequency Droop to slightly shift to the right-hand side of the plane. Now, to summarize, the selection of Droop gains will affect the control bandwidth as witnessed in these eigenplots in earlier slides. The purpose of selecting high Droop gains is to increase the speed of response to disturbances. However, this has a degrading impact on the network stability. Referring to the stability region plot illustrated on the left-hand side of the slide, the combination of KF and KEV gains can push the system to stability or instability can actually push the system to stability by ensuring sufficient damping performance or accelerating the response speed at the cost of driving the microgrid to instability. This is evident in the 2 time domain plots shown on the right-hand side, where a settling time of 0.4 seconds will generate more violent oscillatory dynamics than a system with a settling time of 1 second. Let's have a look at a simple case study consisting of 3 inverters with various frequency Droop settings. Question we should ask is, well, which of the following scenario will generate a more desirable performance in terms of response speed and stability? Now, all the inverters in the first and second scenarios have all the same Droop gains, where the first scenario on the left-hand side is 1%, the second scenario in the center is 0.5% Droop gains. Now, this basically indicates that the inverters will be doing equal power sharing. On the other hand, the third scenario on the right-hand side introduces unequal power sharing. And this will introduce stress to one of the inverter, which is actually not a desirable attribute at steady state. In terms of response speed, though, the first case will have a faster response than the second one due to the higher gains. So to conclude, the setting of the first case is considered as the most desirable among the 3 configurations. under both steady state and also dynamic conditions. We will now look at the impact of the lines interconnecting the grid-forming inverters in the microgrid. This is when things become really interesting. In general, the stability of the system worsens when the line becomes more dominant. This can occur at a higher Rx ratio of which increases across coupling effects, or at a lower Rx ratio where the system lag is increased. Now, Droop control design is not a straightforward job in practice due to the lack of global situational awareness among the individual inverters. The stability problem actually becomes more complex in the presence of multiple grid-forming inverters. Now, suppose we have 2 inverters, and we would like to add a third one to the network. The selection of the Droop gains is a tricky task. The issue is that each inverter will introduce additional poles to the system, where the Droop poles began to interact with each other. In fact, the damping performance worsens as more grid-forming inverters are added to the system, as shown in these eigenplots. To ensure stable operation, the operator will have to coordinate all the local controllers. But this approach comes at a price, and that is the increase in computational complexity of the stability analysis. Basically, the polynomial time complexity is to the order of 3. This can result to scalability problems in larger systems. To maintain stability, the Droop gains should be set adequately based on the number of inverters and the grid topology. Unfortunately, though, the number of grid-forming inverters can vary based on the need of the microgrid. As a result, stable Droop gains for n parallel inverters may not be suitable for n-1 number of inverters for power sharing. The problem can become more challenging when the topology changes, which vary the interconnectivity among the inverters themselves. So now the question is, well, how do you maintain stable operation under all these variables? Now, the stability problem of power sharing among inverters in a microgrid can be addressed by first studying the properties of instability in the primary control. Contributing factors include cross-coupling effects, line dynamics, internal loops of inverter, and stability margins. Now, primary controls are typically executed using distributed control, where the challenges of reactive power sharing and cybersecurity needs to be addressed. Real-time control plays a critical role in ensuring the microgrid can recover from disturbances via near real-time situational awareness of the stability issues at hand. So with those background covered and the problem outlined, I will now proceed to present one of our Droop control design recently developed within our group. The control of a microgrid consists of multiple inverters and can be divided into 2 subsystems. The active power loop manages the active power sharing among the inverters, whereas the reactive power loop regulates the voltage of the microgrid. The stability factor that influence both loops are Droop coefficients and the line and load impedances. An ideal system is when there are negligible line resistance, and each loop is independent and stable for any Droop gains, of which then guarantee the stability of the microgrid. However, in real life, we have to deal with the coupling issue between the P and Q, as well as the lagging system dynamics contributed by the lines. Both destabilizing effects influence the active power and reactive power loops, as shown here. They arise from the incompatibility between the conventional Droop control and the dynamic of the network. To be exact, though, the contributing factors come from the line impedance, which are the resistance and inductance. Basically, the line dynamics introduce a lagging factor. The line dynamics can be summarized by 2 factors as indicated before, resistance and inductance. Firstly, the cross-coupling effect is primarily introduced by the resistance of the line, which forge dependence between PV and QV Droop loops. The resulting impact is a positive feedback at higher Droop gains. Next, the inductance of the line slows down power dynamics and can be viewed as a phase lag in the active and reactive power control loops. Referring to the control theory, a larger phase lag can cause instability under high control gains. Let's first examine the property of cross-coupling effect in terms of line impedance for a single inverter scenario, as shown here. If the line is purely inductive, then active power depends only on the phase angle difference, and the reactor relies on the voltage differences. This is our classic power flow equations, of course. On the other hand, though, if the line is lossy due to the presence of line resistance, then the active and reactive power flows depend on both the phase angle differences and the voltage differences. Next, the electromagnetic dynamics from the lines need to be accounted as well. Suppose we have a simple RL circuit. The transit of closing the switch can be modeled by the following voltage and current expressions. The corresponding response under DC and AC sources are illustrated in the plots on the right-hand side. In these cases, the settling time is proportional to the lag introduced by the line. To summarize the observations made in the previous slides, the cross-coupling effect is attributed by the resistance of the line, and the line dynamics are generated by the inductance of the line. Since resistance is an element with no dynamics, the cross-coupling effect is observable in the static Jacobian matrix of the admittance. In fact, the cross-coupling effect is the dominating factor at high Rx ratio. On the other hand, the line dynamics is only observable in the dynamic Jacobian matrix of the network admittance. Referring to the complete small signal model of a single inverter, the line dynamics can be captured by a second-order expression in terms of rho, or R by X ratio, and the nominal frequency. This destabilizing effect is dominant at low Rx ratios. As we can see, the stability of a microgrid is dependent on the properties of the network, which are no longer can be assumed to be passive. Suppose we now replace the infinite bus with another grid-forming inverter as shown in the center single line diagram. The interaction between these two inverters under high Droop gains will result to unstable power flows as a consequence of these two destabilizing effects. If the line has a high R by X ratio, then the instability is a direct result of the PQ cross-coupling effect. If the line has a low R by X ratio, then the instability is an outcome of the lagging dynamics of the line. These two effects can be represented by these terms in the fifth-order model shown here. Now, the question is, how do we guarantee stability of the microgrid in the presence of these two factors? To start, let's define the meaning of guaranteed stability. A system is guaranteed stable if it can achieve stable power sharing for all Droop gains, any number of inverters as well, and under any grid topologies. Of course, the benefits of achieving such performance is that we can reduce the investment on line stability assessments and allowing operators to make operational decisions purely based on the economic interests. But more importantly, though, is that guaranteed stability for an inverter can realize the concept of plug and play, where renewable operators can connect or disconnect or change their mode of operating their inverters at will. So in literature, issues of cross-coupling has been well studied. And one effective solution is the generalized Droop that we demonstrated in developing a small signal model. These solutions ensure stable power sharing under higher Rx ratio, but unfortunately do not account for the scenarios of the lower R by X ratios. In fact, the notion of line dynamics was only recently reported, and there is yet an analytical approach to mitigate the electromagnetic dynamics. To address this stability issue, we will now present a compensator design that guarantees microgrid stability under any R by X ratios. We will return to the small signal model of the multi-inverter system shown here. The first step is to rotate the power management frame to eliminate the cross-coupling as proposed by the generalized Droop control. The angle of rotation, phi, is governed by the Rx ratio of the system. The resulting transformation matrix is denoted as T, where IN is the identity matrix of size n, and n refers to the number of grid-forming inverters. After some manipulations, we can remove the conductance element G in the bus admittance matrix as shown here. The cross-coupling effect is therefore removed from the generalized Droop control. Next, we need to deal with the system dynamics highlighted in red. The second step is to insert zeros into the Droop control loops to compensate the phase lag introduced by the line inductance. As a result, we can cancel out the lag factor of the system dynamics from the small signal model. In essence, the destabilizing effect of the line dynamics can be addressed by a compensator. We shall modify the existing low-pass measurement filter into a leak lag compensator. The compensator should provide the exact phase lead to nullify the phase lag of the lines. The proposed filter is expressed as f of s, where tau s plus 1 is a dummy term inserted to ensure the transfer function is causal. It should be set with a sufficiently small time constant, much lesser than Tc. The frequency response of the proposed filter is illustrated in the Bode plot, where a boost in the phase lead is provided in the Droop control bandwidth of interest. Furthermore, a steady state, or s equal to 0, the filter has a unity gain. Therefore, the proposed filter does not change the steady state power flow. Since the filter is a software modification in the inverter control, no hardware modifications are required to the existing inverters and the overall microgrid as well. This design can be directly incorporated into the existing systems without any retuning of the existing Droop values. In addition, the properties of the generalized Droop is not compromised by the design, as a filter is still dependent on rho. More importantly, the proposed filter is independent to the operating point, Droop coefficients, and the location of the source. Referring to the overall control structure, we can see that the proposed filter is able to address the cross-coupling and line dynamics at the same time. In fact, the proposed control design does not require the need to heuristically find suitable Droop coefficients to guarantee power sharing stability. Instead, the user has the freedom to select any Droop settings without the fear of destabilizing the microgrid. Let's compare the closed-loop response of the proposed filter against the conventional filter used in the generalized Droop control. Referring to the eigenplots, an increase in KF will result to the poles moving to the right-hand side for the conventional filter case. Whereas the poles move towards the left-hand side of the plane using our proposed filter, as shown on the right-hand side eigenplot. Theoretically, there is no upper limit of the Droop gains for stability. That said, if we increase the Rx ratio, these poles will begin to move to the right-hand side. However, they will ultimately align themselves on the vertical line governed by the low-pass filter time constant due to the diminishing effect of the lagging factor. This vertical line is always located in the left-hand side of the plane, and thus ensuring the stability of the power sharing in the microgrid. Another way to visualize stability improvement is to plot the stability regions of various combinations of KV and KF Droops. Here, the combination outside the stability contour will result to unstable power sharing. The dimension of this control hyperspace is 2n, where n refers to the number of grid-forming inverters in the microgrid. So for the case of a single inverter, we have a 2-dimension hyperspace as shown here. As we can see, the stability region for the conventional filter is highly dependent on the Rx ratio of the network. whereas the proposed filter allows the operator to select any Droop setting and thus simplify the stability assessments. Suppose we implement the Droop control into a 5 grid-forming inverters within the microgrid having an arbitrary grid topology. The microgrid responds to a step change of 0.1 per unit increase in the load at 0.2 seconds is shown in these plots over here. From these simulation plots, we observe that those using the proposed filter is able to promptly damp the oscillations. Now, the same conclusion can be drawn when we use an experimental setup. The experimental results are shown in these 2 plots over here. In this case, the performance of the conventional filter is unstable after a step change in the KF Droop gain. In contrast, the proposed filter is able to adjust the new Droop settings with ease. To summarize, the destabilizing effect of the cross-coupling and line dynamics have been resolved using a simple compensator design that is coupled to the generalized Droop and control loop. The design is deterministic and remove the past need of heuristically tuning the Droop gains and running an exhaustive stability assessments. So this comes to the conclusion of today's seminar, which can be summarized as follows. Power sharing is an important function among inverter-based generators within the microgrid. When the microgrid is operating in autonomous mode and adopting a decentralized approach to manage its generations, then the stability of the microgrid may be compromised by inadequate Droop settings. In essence, Droop control are used to provide inverters with the ability to regulate the voltage and frequency in the absence of the main grid. However, the challenges in the Droop control are its ability to guarantee stability and adaptively adjust its gains to meet the changing operating conditions. The design boils down to tackling the destabilizing effects imposed by the PQ cross-coupling and the line dynamics. These effects have bothered operators, and past efforts to retune Droop gains resort to the time-intensive effort of heuristically, with trial and error, choosing the Droop gains and then running the stability analysis to ensure the overall system stability. Such approach is less efficient and, more importantly, lacks the theoretical understanding of the power sharing properties among grid-forming inverters within the microgrid. To this end, a method to ensure stable power sharing under any Droop gains, any number of inverters, and any topology has been presented in this seminar. The proposed compensatory is coupled with the generalized Droop to remove the cross-coupling and line dynamic effects. The compensator design also enables operator to change the connectivity and operating mode of the individual inverters at will, and without the need to run a full system stability analysis. This realizes the concept of plug-and-play inverters within a microgrid. So further details regarding to the modeling of a microgrid and design of Droop controllers and microgrid stability can be referred to these research papers published by my group in the last few years. And finally, to conclude, I would like to thank NIT for organizing today's seminar. Thank you.
Yeah, thank you so much, sir, for a
I hope it's not too dry.
No, it was a very, very informative session, and I think all the participants enjoyed the session. Because later you can see the link, YouTube link, you can see like a lot of like appreciations are coming for the session. Yeah, and we got like 1 or 2 questions, like
Sure.
in that, like, yeah, one question I'm just posting in your chat box, sir.
Okay. Hang on, just let me have a read first.
Should I read out the question, sir?
You can read it out. Yeah, I'm just trying to understand what is. Yeah.
Fine.
So the question
Actually,
is.
this is the question. To investigate the islanding operation, is there any condition for Q factor value selection? Q factor value selection, like if the load is RLC parallel load.
Can you provide more information on this, or?
No, actually, this is a question posted by a student
Okay.
who is working on an RLC parallel load. He is asking like, if like what will be the Q factor selection, like R by X, X by R, that ratio, how he can choose for investigating islanding operation.
Actually, I'm not exactly sure what the question is trying to ask me. So it's a Q factor selection. So
Pranesh,
just ask Pranesh. Do you understand what the question is trying to infer?
Mic is muted, Pranesh. Please unmute yourself. Pranesh, please unmute.
Yeah. Okay. So I'm not exactly sure where what kind of dynamics the person has been looking at, but I can answer this question with reference to the model that the Professor PEng just talked about, particularly with respect to Droop control. So under Droop control, we always see that the stability is dependent upon the interconnection line admittances, right? The impedance of these lines, the impedance magnitude will be typically very low because we don't want a large voltage drop across these lines. So as a result, we see that the admittance, the inverse of the impedance, is generally very large for the interconnecting lines. So with respect to these admittance, the admittance of the load will actually be very, very small. In other words, unless there is a fault, the load impedance will not affect the dynamics of the system, right? Because it is very easy to verify. If we look at the Jacobian matrix, for example, in terms of the power flow Jacobian, we will see that the load impedances contribute very little. Generally, in power system analysis, we don't necessarily care about the Z11, Z22, and so on, because those impedances are really the impedance are very large compared to the lines. So whatever be the Q factor of the load, be it a purely capacitive or purely inductive or purely resistive load, or any combination of these, it is not going to significantly affect the stability. What will affect the stability is when you have constant power loads, because constant power loads tend to have a negative incremental resistance. So the negative incremental resistance has been shown in some papers to have a bad effect on the stability, but even that is not very significant. So the load when it can be ignored.
If it's talking about load, I mean, generally, it's constant power load could have an instability, but I mean, as Pranesh has said, many papers recently published has demonstrated that it has little effect on the overall stability in terms of power sharing. Yeah, but I'm not exactly sure by the question, but I think this is the best we can answer.
Yeah, since the dynamics part is not clear. Yeah, like if the student is having any further query, I'll ask him to write so that we can share with you, sir.
Sorry about that. It's just a bit too broad for me to give an exact answer. Yeah. So what's the?
Yeah. Then only one more query.
One question from my side. Okay, I am Dr. JP Mishra from Electrical Engineering Department, presently working as HOD. But this is related to my area, little bit my area of work. But my question is, how do you, in the coordination control, suppose you have to do the, you have to design the KP and KV with coordination control. That is, with respect to that, for individual inverter control, okay, you can. But how do you coordinate? And how do you coordinate the design of this KP and KV in case of? How you are going to analyze for designing this KP KV of each inverter?
So first of all,
coordinated control environment.
A coordinated control environment. What we're doing here is we're taking as we said, it's a decentralized approach. So everything is operating as a primary control, and then of course you can add a secondary control loop to reset the Droop gain. After it has finished. Exit the transient situation. In terms of coordination, there's many different ways we can tackle the problem. But I would say a simple coordination. Panesh, do you have any suggestions? I would say just use distributed control, but so, I was wondering.
I think the exact point the professor was making is that for a single inverter system, it is easy to choose the Droop gains, but when you have multiple inverters, they interact with each other. So necessarily the stability limits may not be the same. So the advantage of using a control scheme such as the one we have proposed is that there is no need to coordinate. The system is guaranteed to be stable. So if you look at the models that Professor PEng has presented, they're all in matrix form. So they are not necessarily just for one inverter. They model all the inverters Droop control, and they model all the interactions as well, because the network we have modeled as G and B, which is the elements of the Y bus matrix. So that includes already all the interactions. So whatever results we get from our model that we have proposed will already include the interactions that you're talking about. So we don't have to necessarily redo the model. So that is the beauty of working with these kind of models in matrix form instead of state space. If it's a state space model, you basically need to include like double the number of states, triple the number of states, and then observe the very complex dynamics. So you cannot make any sense out of that. Instead, it is way more advantageous for you to look at the Laplace domain in a characteristic equation, matrix characteristic equation form, which helps you to look at the dynamics, but with a conceptual understanding rather than just a numerical understanding. So all the interactions you can understand from that perspective. So we don't have to model anything separately for a multi-inverter system.
Is there any common index control index parameter? So that is your specification. That means you can specify in terms of index, so that stability index.
Yeah.
So that you can at least correlate the relative stability.
Definitely. So I think that's a very interesting point, and we have exactly a paper on this where we looked at the sensitivities of each inverter. So all the inverters, even though they may have same or different coefficients, Droop coefficients, only depending on the topology, certain inverters have more contribution towards instability than others. So we have defined a sensitivity criterion, which I don't think the professor has presented today.
No, we haven't. But it's basically we rank the inverter, grid forming inverter, in terms of which was more critical, and that allows you to address that particular one.
So
it's in the list of the references. I think we'll share the slides later, but it's in the last slide. We have one paper on this transactional smart grid, which talks about the selection of inverters in an online manner. And that allow you, I suppose, in your term, coordinate which one to address first. But with the compensator filter we designed in this, talk about in this seminar, is independent. You can set any Droop setting you like, as long as you have the network administered model, it will do the job for you. Yes.
One more question: what is the effect of virtual inertia control in this respect of grid forming inverter? Virtual inertia control in this grid forming inverter. Yes.
Virtual inertia or virtual, the generalized Droop, you can also modify this into a virtual inertia. I mean, all you do is just modify the equation, take out a Droop, and replace it. And basically, the concept will still works. Like, you can still allow it to tune and guarantee stability. What the beauty of this model is looking at decoupling the effects of cross coupling and the line dynamics. That's what it is. And it can be used even for, like, you got virtual inertia with virtual impedance, with Droop. It can all be used in that kind of manner. It's the approach that we are proposing over here. Thank you.
Sir, one more last question.
Oh, yes, please.
Because this is my area of interest, so I want to ask.
It's great. Yeah.
So as the inverter is, this is a grid forming inverter.
Yes.
Whether that out of this current control loop as well as voltage control loop, I think impact of voltage control loop is more important as far as compared to current control loop, because it is a grid forming inverter and you have to maintain certain voltage level. So is it so as far as the impact is concerned, which loop is more impact? It will give more impact in the form of that is your grid forming inverter.
I think I can answer in a different way. Is to say, if we have ensured timescale separation between the Droop loop and inner loop and outer loop, all these three timescale separation, then the interaction of the poles actually don't exist or have minimal impact. And that way we prevent the instability, as you have mentioned, would be triggered by the inner or outer, we can remove that. But of course, this is based on, you have to make sure you have, as we have suggested, a magnitude of 10. That would do this job. Obviously, in literature, some researchers have probably used inverters with switches with a smaller control, a lower band switching band, and then this control could have happened, could interact. But basically, in modern technology, you buy these MOSFET, sorry, not MOSFET, IGBTs or gallium nitride switches. But the chances of you hitting this is probably not likely, as long as you ensure timescale separation. Yeah. So my answer is that you probably don't need to worry about it as long as you follow the right control bandwidth design. Yeah.
Thank you, Professor Jim Peng. I may interact with you in my any
absolutely
program.
Absolutely.
So, thank you very
I do
much
hope this will be a good outreach for you guys to have give us suggestion as well. I mean, the paper we've listed for this talk is a recent paper on power system, transactional power system, and we do hope that we believe we tested out, it has practical applications. We do hope if industry partners could also try it out. Just a simple filter design. It's more like designing your power system stabilizer. That's how we come up with this approach. A compensated design for conventional power system, or why can't you do the same for a microgrid when you're doing power sharing? So yeah, we're definitely open to discussions. I mean, in fact, in academia, the beauty is the discussion. If you all work in our own silo, we're not going to progress very well. So I'm more than welcome to have discussion. I have a question. What? Okay, I have a question here. No, thank you, sir. Thank you. So in the cybersecurity issues, for some of my paper recently, there's a question about what kind of cybersecurity issue in a microgrid operation, and that could cause stability issues. So in some of our recent paper, what we have been discussing is that, if you tamper with the sensor by injecting data, false data into the sensors, then it is possible to cause an unstable power sharing in a microgrid. And you might argue, well, why is it easier to hack a microgrid in a sensor? Well, basically, microgrid is a collection of parties, put together the devices and have an operator operating it. So the security investment in a microgrid is a lot less than, let's say, a conventional power utility. So that's why it is more easier to hack a microgrid in terms of sensor or the communication itself. So communication, what you can do if you want to hack a microgrid, if you're doing this kind of research, it's simple. You could do a denial of service, that will cause communication to fall apart, or you can inject false data, by randomly select data to inject or replay, use the recorded data from previous situation and then feed it into the system to bring down a microgrid. So microgrid research with cybersecurity is kind of a hot topic over the last 2 years, and so I have some research ongoing in this field. And right now, the focus of this kind of research, based on this question, I'm assuming that someone's heading down this research. So the focus over here you should look at is, well, what are the more plausible situation? When I first started security about 5 years ago, I looked at a phasor measurement unit, so the high voltage, the PMU. But back in that time, they were concerned after Ukrainian grid was attacked. But in the last few years, vigorous studies has been done in the utility to find out that it's pretty difficult to hack a sensor in a substation. But on the microgrid side, this has become plausible because of the openness or less security requirement installation. So if you're going to look at the microgrid research with security attacks, then you should look at what are the plausible situations that are unique to a microgrid and not common to a power system. If you look at a common scenario, it'll be difficult to justify why this is suitable for microgrid case study. So that's what I think, and I don't know the other question. This other question is
possible. ...
So it's high RX ratio, it is possible to still apply Droop control. That's what we have shown. So we've shown with our control compensated design, you can deal with high Droop, high R by X ratio or low R by X ratio. Punish, do you want to add anything?
Yes. So I think the question has been is if the X divided by R ratio is high. That means, see, let's take two cases. Okay, purely inductive system, which is very low R/X ratio, and a purely resistive system, which is very high R/X ratio. So for purely inductive system, the conventional Droop control is ideal because there is no conductance or resistance, right? The system remains stable for all Droop coefficients without having to do any special type of compensated design or any generalized Droop. Just the conventional PFQV Droop that we use for power systems is sufficient, because that is the entire reason why the power grid today is working safely, right? They may have some rotor angle oscillations, but nevertheless, usually they are quite stable.
Yeah.
Now, if we take the other case, purely resistive microgrids. So purely resistive microgrids, let's say the inductance is very small. In that case, the active power flow is strongly dependent upon the voltage, and the reactive power flow will be strongly coupled to the frequency as well. So there's a highly cross-coupled system. Now, if you look at our generalized Droop control, why we call it generalized? It is because there is a rotation angle that can be selected depending on the R/X ratio. So if you actually look at the rotation angle for a very resistive system, that rotation angle will be close to 90 degrees. That means basically you're not doing PFQV Droop, you're doing PVQF Droop. So that is one simple case of a DC microgrid. In a DC microgrid, you have PV Droop. You don't have the concept of reactive power and frequency, but so the very high resistive system is equivalent to a DC microgrid. So yes, Droop control is possible. You just need to see if the network is resistive, then the P depends on V. So your Droop control must also reflect that fact. So as long as your controller reflects the system's behavior, then you will have stable behavior. Otherwise, you will not be able to maintain stability for any Droop coefficients. Hope that clarifies. Yeah.
Okay, yeah. So, I mean, based on the question, I think we can assume an answer. And just one last thing is that since I talk about security, I will share a link over here to one of our recent paper, which is on in +1, and I think this is a new frontier to look at security. These days, you look at security, many people focus on hacking the hardware or software, but to close the loop is actually the humans involved. That's us in a deregulated environment. What is vulnerable? Our human behavior. How do you manipulate us through disinformation campaign? And that's what this paper I shared in the link is telling us. It's a recent work we did, which look at weaponizing disinformations to bring down a power grid. We demonstrate how it's possible to cause pockets of network having a blackout in the greater London city. And it's just so this is a combination of social science and computer science with power engineering combined together, which I think will give a better impression for those who are interested in cyber attacks. This will give you a better understanding. And maybe next time we can give another talk on this. This is, so I'll do two things. One's on microgrid stability, another is on grid security from the cyber war. Basically attacks, any form, behavior attacks, cyber attacks, data attack, that kind of stuff. Yeah. So yeah, thank you. I mean, that's all we can say. Then, Panesh,
if anybody is interested, they can find the preprints of all these papers, the free version of all these papers on our website. So all you have to do is Google our laboratory's name, and you can find all the links to the papers and a lot of, we even have simplified descriptions from our papers, so for ease of understanding.
Right.
So just an advertisement for our group.
So, and I just want to conclude that if you know, Panesh is also an NIT graduate. He does his bachelor degree from NIT Trichy. So, I mean, I think any NITs are, it's great to work with you guys if there's an opportunity to arise. Yeah, thanks. And thank you.
Thank you so much, sir. Nalin sir, please.
Yeah. Thank you, Professor PEng.
No, thank you
for your valuable comments and nice presentation. We have listened throughout, and I hope this will help and find out some new avenues for new research and collaboration to all the listeners. I hope to have some good collaboration and active participation in near future with you and with your laboratory. Thank you very much.
I do. Thank you. Thank you.
Yeah.
Thank you so much, sir. Thank you so much for once again for accepting our request and for spending your valuable time here. It was a very informative presentation.
It's a pleasure. And yeah, I mean, it's sharing research, and hopefully, you guys can have a trial of our filter and see if it works for you or not. Yeah, any problem, do give us a call. We will be more than happy to help out and also share our insights. Thank you.
Sure, sir. Thank you so much, sir. Thank you, Pranesh. Thank you, Pranesh.
Sure, it's my pleasure.
Okay. All right then.
Zifran
Yes,
Raman, thank you very much. Then Asa madam, should we conclude this way?
yes, yes, sir. Yes, sir. Please, sir.
Yes. Now, thank you very much, all the participants to attend the session, and I hope you have already shared the feedback and you have received also, ma'am.
Yes, sir.
Yes.
We are receiving. Yes, sir.
Yeah. Then I can conclude here. Thank you very much. Thank you for your time.
Thank you.
Bye bye. Have a good day, sir.
Thank you. Bye.
Have a good day, sir. Thank you, sir.
Bye-bye.
Thank you, Nalin, sir.
It's fine.
Take-
It was excellent.
Yes, sir. Yes, sir.
Thank you, madam. It was a very nice.
Yeah.
Congratulations. Congratulations, sir. And Vidhi sir, congratulations. Asarani madam, congratulations.
Thank you, sir. Thank you, sir.
Bye, ma'am.
Bye, sir. Thank you,
Award
Abad,
is
sir,
there.
for joining.
Award.
Yes, sir.
Very good.
Bilal, sir. Good afternoon, sir.
Ma'am, share your link so that we can send the feedback form.
Already shared, sir. Already shared in the YouTube. Here,
Madam,
here.
I have joined in the Google Meet.
Yes, sir. Here I'll share
That's
again.
why.
1 minute. 1 minute. 1 minute.
Okay, ma'am. Then I just log out.
Please, sir. Yes, sir. Thank
Bye-bye.
you so much, sir. Thank you so much, sir. Take care,
Bye-bye.
sir.
Bye-bye.
Bye-bye. Yes, sir.
Bye.
Thank you. 1 minute, sir. Awad, sir. 1 minute.
Yes, yes, Betty ma'am.
Yes, sir.
Alpha ma'am is not there, madam, I think.
What, sir?
Alpha madam is not there.
Yeah. She was there for some
forget.
time.
Yes, yes.
I'm posting in the group here, sir. Thank you, Dulal, sir. Sir, posted here. Can you see, sir?
Madam, I am listening whole presentation from
Yeah.
beginning to
How was it, sir?
It's fine, madam. I'm also sharing some questions so that we can ask,
Yeah.
get
Yes,
some
yes.
input from that side.
Yes, sir. I
Okay,
have
madam.
shared the
Thank you.
Yes, sir. Thank you so much, sir. Good afternoon, Chan, sir.
Yeah, feedback form. This is similar kind of thing, madam.
Yeah, similar, sir. Similar how we made the other one, similar one.
Okay.
Yeah, same. Yeah, so thank you all participants for patiently listening this session. I think it was useful for you. So those who are working in this area, please kindly you can download this one again and please listen to it and let us know if you are having any doubts. You can mail to us. And like regarding the what is that certificate, we can see some queries here. So after reviewing your feedback form, and feedback form indirectly tells the attendance. Based on that, we will be sharing the certificates in 2 weeks time. Okay. Thank you all. Once again, thank you. Thank you for joining this program. Thank you for registering and joining for the program. Take care.